The gradient is a new operator that's going to tell us about the slope of surfaces. Now we kind of already have an idea a little bit about the slope of surfaces, because if we have, just real quick, if z is some function of x and y, that gives us some three-dimensional surface. And we know the partial of z with respect to x tells us about the slope of this surface in the x direction when we fix a specific y value. But we need something a little bit more general if we're going to talk about the slope on a surface. So our brand new operator looks like this. Now the way that you read this, it's an upside down triangle. We're going to read this as del f. So you just read that as del. It's a Greek letter with nabla, I think is the way you pronounce it. But we always read this as del. So del f, here's what the operator actually is. It says take this function, take the derivative with respect to x in the I direction, and then take the derivative with respect to f the x direction in the x direction, and the derivative with respect to y in the y direction. Now notice this gives us a vector. So think about it like this, f sub x, f sub y. All right, so we got a brand new operator. Of course, the del operator expands. If this was a function of x, y, and z, we'd have an f sub z in the z direction, or so on and so forth. Now, what does this operator actually tells us? This gives you the direction of maximum increase. Okay, and the magnitude of that, the magnitude of del f, will be the maximum increase itself. Or kind of think about it, the slope, the maximum slope you could have leaving that point. So let's just take a look at a couple real quick pictures, kind of the idea. Let's define something real quick. Let's do f of x and y is, I don't know, 4 minus x squared minus y squared. Now again, this is a shape we've seen a lot for a couple of reasons. One, it's very easy to understand, and two, it's one of the few that I can kind of draw. This is a paraboloid, kind of looks like this. It's shifted up here at 4, and in the xy plane, that's a circle of radius 2. So let's actually see if we can use the operator first. So first off, let's say if I said find del f. Well, del f will be the partial with respect to x, comma the partial with respect to y. So if this is f, the partial with respect to x will be negative 2x. Partial with respect to y will be negative 2y. All right, so that is the gradient of our function. Now, what is this actually telling us? Well, this is where it kind of gets not necessarily abstract, but a little bit hard to see. Let's say, I'm going to now draw a two-dimensional picture, x, y. Let's say that this is the xy plane directly below this upside down bowl. And I wanted to look at the point 1, 1. So in this picture, imagine over here that there's a point 1, 1 right about there. And if you go up, that point exists on that curve. So if we plug 1, 1 into this, we would get a y value of 2, right? So that's the point 1, 1, 2 on the surface. So let's say you're standing on the side of this hill. What direction would you have to walk for it to be the steepest as possible? We can think if you walk kind of left or right here, you'd kind of be walking around the hill. So to be the steepest, you'd have to walk directly up the hill. Well, notice here, if we take our gradient, del f, and we evaluate it at the point 1, 1, we'd end up with the vector negative 2, negative 2. So think about that from here. If that's our point 1, 1, negative 2 points in that direction. Now it's hard to see in this picture, but it points straight through the origin. So this says if you were to walk towards the origin, that would kind of be facing, that would be walking straight towards the top of the mountain here. That would be the direction of the maximum increase that you could do. Now, of course, the opposite of that is the negative, walking exactly the other way. 2 would be walking that way. That would be the minimum increase, basically the most negative. So that would give us the direction of the most increase. Now, what would kind of the idea, what would the slope be if we headed in that direction? Well, the magnitude of del F, so the magnitude of this would be the square root of negative 2x squared negative 2y squared, or of 4x squared plus 4y squared. Now, the magnitude at that point, at the point 1, 1, of course, would be 4 plus 4, or the square root of 8. So, if you were standing on that point, the point 1, 1, 2 on this surface, and you started walking straight to the top of the hill, that would be the steepest you could possibly walk, the slope at that point would be the square root of 8. So the gradient tells you the direction of the maximum increase, and of course, if you put a negative in front of it, that would be the opposite direction, right? That would be the least increase or the most negative increase. Now, this gradient also gives us something fairly interesting as well. The gradient is always perpendicular to the level curves. Now, think about this. This one's a pretty easy shape. If you were to take this and we start doing the level curves, we start picking z values and we start slicing this thing at different z values, we're just going to get a bunch of circles. So for this one, level curves would look something like this. It'd be circles like that. Now, this should be easy for you to see. If you're standing anywhere on this surface, and I said, what direction would it be the steepest if you started to walking? You'd always be walking towards the top of the hill. Well, the top of the hill's shown by the first dot right there in the middle, which means anywhere you're standing here, the direction is always going to be straight towards the middle like that. So you can see it doesn't matter which level curve you're standing on, the gradient would have to point that way. Now, just obviously, since all those are in a radial direction, they're all normal or perpendicular to those level curves. Now, we're going to see how that's useful quite a bit a little bit later, but let me kind of give you a hint. Remember when we first saw level curves, we said if we took this as z equals 4 minus x squared minus y squared, I technically can move all that to the other side. Kind of seen this a little bit before. If I were to write it like this, 0 is equal to 4 minus x squared minus y squared minus z, you can define some new function here. Now, this is no longer a three-dimensional surface. This is now a four-dimensional surface, which means the level curve is actually this surface right here. So if I were to find the gradient of this, that would have to necessarily be normal to this surface, which means now we have another tool to help us find normal vectors to surfaces other than the cross product. And it's going to be much, much easier to use. So in future sections, we're going to see to find the normal to a surface, we're going to move all the variables to one side and find the gradient of that. And that will give us a normal vector. All right, so far we've seen if we take the partial of the original function with respect to x, that gives us the slope in the x direction. The partial with respect to y gives us the slope in the y direction. And now we have this new operator called the gradient, which tells us the direction that the slope would be the maximum. But none of those are very, I can't think of the word, unique. What I mean by it, they all are unique. But what if I wanted to be more general in this? What if I wanted to say, let's say I was standing on the surface at this same point, and I want to walk in a random direction. Let's say I wanted to walk in that way there, and say, how steep is it going to be if I just start walking in that direction? Can I find the slope in any generic direction that I want to? And the answer is actually yes, and it's called the directional derivative. The directional derivative will give you the slope in a given direction. So not a fixed direction that we know about, say the x direction or the y direction, or even the direction that has the maximum increase. But what about any arbitrary direction? Well, let's see. All we're going to have to do is we're going to, here's the way we're going to define it first off. So this is the directional derivative of f in the u direction. So u, to state what the direction we're going to move in, we're going to use a vector to say we're going to move that way. So the way that we're going to define this is fairly simple. We're going to find the gradient of the function and just dot it with u hat. But remember, when we dot something with a unit vector, the only thing we get is how much it points in this direction. So this will give you the slope in the direction of the unit vector u. Let me go ahead and write that as a unit vector. So if you're not giving u as a unit vector, you're going to have to well, find that first. So let's try a quick example of this. Find the directional derivative of f of x and y is equal to 2x squared minus y cubed, and the direction of 3, 4. Okay, so first off, let's see what this actually entails. What are we actually talking about here? So we have some three-dimensional surface here. There's our XYZ plane, our XYZ coordinate system. Now, I'm just going to sketch something nonsensical. I don't know what that looks like. So let's just say it has some shape up here. Who knows? It's some three-dimensional shape. So down here in the XY plane, notice this is a two-dimensional vector. So in the XY plane, we have this vector 3, 4. So we want to find the directional derivative in the direction of 3, 4. Let me just go ahead and say at the point, let's do 1, 1, 1. All right, so what do we mean by that? So if I come up here to the point 1, 1, 1, that's some point on the surface, right? If x is 1, y is 1, that means u would be 1. So that's a point on that surface. Now notice I can walk away from that point in any direction that I want. But let's say from that point, if you look right above it, that's the down there in the XY plane. If I were to walk in the direction x is 3, y is 4, I would kind of be walking that way. Kind of be walking that way. Sorry, kind of that way. So I'm kind of walking down this way. What would the slope be in that direction? Well, first off, let's find the directional derivative of f in the u direction. To do that, I have to have del f and I have to have u hat. We need these two things because we know by definition this is del f dot u hat. So del f would be the gradient of this, so it'd be the derivative of that with respect to x in the x direction, comma the derivative of that with respect to y in the y direction. So there is the gradient of f. What is the unit vector for u? Well, I'm going to skip a step here. The magnitude of this would be the square root of 3 squared plus 4 squared, which ends up being 5. Don't believe me? Verify that for yourself. So the directional derivative of our function would be del f dot u. So that's going to be 12/5 x minus 12/5 y cubed. Okay, so there's our formula. So this will tell us the slope anywhere on the surface above the xy plane. So here we'd have to plug in our x and a y value to figure out what our slope is. So I said at the point 1, 1, 1. So at the point 1, 1, 1, this would actually be, I'm going to squeeze it down here, at 1, 1, or 1, 1, 1 would actually be 0. So apparently it's flat right there if we were to walk in that direction. Pretty interesting, I wouldn't have thought that. All right, so the directional derivative gives you the slope in any direction u, but you gotta remember you gotta make u a unit vector to give that. And what it gives you the equation for the slope if you were to walk in that direction on that surface. Now, since u has to be a unit vector, there is a common way that we represent u. The vector u in the directional derivative is commonly represented as u, or u hat, is cosine theta sine theta. Now, of course, the theta is the exact same theta that we've been using all semester. It's in the xy plane, measured from the positive x-axis there. You can obviously see that this is a unit vector, right? Square them both, add them up, take the square root of it. Now, the nice thing about when you use a u in this direction, you can use an angle to say which direction we're going to turn. So you're saying, okay, I'm standing on the surface here, and I want to turn, kind of on the horizon. I want to turn 30 degrees in this direction and start walking. What's the slope going to be? So if you do it like that, you'll see some textbooks that actually define the directional derivative as this. We're going to go ahead and use our u as a unit vector. So it's going to be the partial of x cosine theta plus f sub y sine theta. Some textbooks actually just go ahead and define it that way. I prefer to keep it a little bit more generic, where u is any unit vector instead of a specific one. So the gradient operator now is never going to go away. It's now a new tool that we're going to use for the rest of the semester. Remember, the directional derivative tells us the slope, just the magnitude of the slope in any given direction.